Did you know you can solve statics truss problems without a calculator, just using a ruler and a protractor? So first, a super quick mini lecture so that you learn how to read Bow's notation, and then I'll do a complete walkthrough for this truss, solving it using a graphical technique, which is how they used to do it back before calculators existed. And they were building bridges and skyscrapers in the 1800s. So engineer Robert Bow decided to label his trusses by labeling the gaps in between the force members. This is completely different than what we do today. When you use method of joints and method of sections, you label the joints on your trusses or frames, because if you're doing method of joints, you need to draw a free body diagram at each joint. If you're doing method of sections, you're going to be doing a sum of moments around the joints. So either way you want to analyze your truss or frame, you need to know where the joints are. But for graphical techniques, you actually track the spaces in between each of the two force members, which sounds really bizarre until you see it in action. So for comparison, I've already solved this truss using the method of joints. So you'll see that I called the top left angled member tension 1, 2, because it connects joints 1 and 2. But on Bow's notation, this is going to be AF, because it's the force member in between space A outside the truss and space F in the middle. And the horizontal member down in the bottom right is going to be tension 4, 5 on my method of joints. But when I do the graphical technique, I'm going to call this TCH, because again, it's in between C and H. And last example, one of these diagonals in the middle, I'm going to call tension 3, 5 when I use method of joints, but it's going to be called GH when I use the graphical technique. So it's not actually that hard, it's just completely new and confusing why we would ever want to do this. There's going to be 3 phases to implementing this graphical solution, and you'll notice that I cheated a little bit and I already solved for the reaction forces. So I've got my 143.3, 56.7, and 100 already labeled in purple. I'm only solving here for the internal forces within each of the members. First part of the graphical technique, I'm going to go around the outside of the truss and place A, B, C, and D, and E as points on my drawing. So I'll start arbitrarily at A and see that when going from A to B on my truss, I pass a 100 Newton force pointing to the right. So I draw a line going to the right, 100 Newtons, going from A to B. Now B goes all the way around, and from B to C, there's that purple upward 143.3. So on my drawing, I go up 143.3 from B up to C. C to D, down 200. So now it's 56.7 below point B. I go back up 56.7 from D to E. So E is at the same place as B. And to confirm that we actually did this correctly, from E to A, I need to go left 100, and good. That brings me back to A. That helps confirm that I did not make any mistakes when I calculated my reaction forces, because the sum of all external forces acting on the truss have to add to 0. So as you add up all of these forces, and that's what we did. We just did a vector addition of adding up all the external forces. We added them all up and we ended up back where we started, just as it has to. Hey, Serenity. All right, your TA Serenity is both lonely and cranky. She doesn't like being left out, but she also doesn't like being lifted up. So we'll see how long she decides to stay up here. All right, so next to find the internal spaces F, G, and H. We're down 1 kitty, but TA Serenity is still with us, so we'll keep going. So first, F and D on my figure are separated by a horizontal force member. So that tells me that F is going to be horizontal from point D, so I can draw a horizontal line. F is separated from point A by this 60-degree angle. So I can add to my drawing a 60-degree line, and where these two lines meet, that is where point F is located. And here comes the crazy black magic of this whole thing. If you measure the lengths of these two lines, 65.5 and 132.7, you'll see that these two lengths perfectly match the values that I solved earlier from method of joints. So all you needed was to draw a perfectly scaled drawing with the perfect angles, and you can measure these lengths with your ruler and solve for the magnitude of each force. And it doesn't just give magnitude, it also can tell you whether these are tension and compression, but I have to come back at the end. Let me finish the drawing first. All right, so let's do point H next. It's going to be a little easy because it is horizontal from point C. So this is going to be way up here at the top of the drawing. It's at a 60-degree angle from point B. So I draw my 60-degree, and again, where these cross, that's going to be point H. And I can find now the force in BH by measuring the length of this line, the 165.5, and I can find the force in CH by measuring the length of the horizontal line, 62.7. Again, compare back to the method of joints, and these two forces match the ones we found from method of joints. It took a bunch of sine and cosine and a whole bunch of free body diagrams to do it via method of joints, and here I'm doing it graphically just by creating lines at the right angles and right distances. It's super cool and bizarre. So we know point G, right in the middle, is separated from point B by a horizontal force member. So it has to be horizontal from B. And then it's also separated from F and H that we already found by a 60-degree line. So we draw these two 60-degree lines, and where all three of these cross, that is point G. So measure the length of these three lines, 65.5, 165.5, and 165.5. Again, every distance that we've solved on here matches perfectly what we found via method of joints. So why don't we actually use this more? It's because we have calculators now. Method of joints and method of sections are probably better, faster methods almost every time, but it's cool to learn a little bit of the history as to how engineers did their jobs back before we had modern tools. Okay, so what about tension or compression? The AutoCAD drawing gave me a perfect value for the magnitude of the force, but it doesn't tell me whether it's tension or compression. Is it a positive or a negative value? So here, let me draw this little clockwise circle around this top left point where the 100 Newton force is. So looking at my sketch, when my clockwise arrow passes through the horizontal member from B to G, it goes from B to G when I work around this joint clockwise. So on my drawing, to go from B to G, I'm going left. So that means the arrow is pointing left, which means this member is in compression. A compressed member is pushing outwards to try to grow back to normal size. When I go on my drawing from G to F, I have to go down and right. So GF, I now put an arrow down and right, meaning this piece is in tension. It's been stretched and is trying to pull back towards the middle. Going, again, continuing clockwise from F to A. On my drawing, F to A goes up and to the right. So my arrow up and to the right, which means this one is also compression. And I can compare back to when I solved these from method of joints, and these two compression members were negative values, and my tension member was a positive value. All right, let's do another joint to show this wasn't a fluke. Starting over on the now top right joint there, when I go from B to H, again in this clockwise direction, on my drawing, B to H is going up and left. So that means the arrow's up and left. This piece is in compression. From H, continuing clockwise around to G, I'm now going down and left. So this piece was in tension. And then G to B, continuing clockwise, G to B goes to the right. So now this member that we already found from the other joint, we are confirming we actually got the arrow to go in the different direction this time, which of course it has to because internal forces cancel out. And we have confirmed, put a little check mark here, that BG is in fact in compression and it is pushing outwards. If I choose the bottom middle joint, then I can find all the last remaining members. So I'm starting here from H to C, moving clockwise. On my drawing, H to C goes to the right. So draw my arrow to the right. From C to D, it moves downwards, which makes sense. The 200 is pointing down. From D to F, I am moving now to the left. So again, put my arrow to the left. From F to G, I am now moving up and to the left. And then lastly, G to H, up and to the right. So these last ones, D to F, F to G, G to H, actually all of them, all four joints here, they're all pulling. Basically, all of these are in tension. They're all being stretched. And so they're all trying to pull back towards the middle of each of these members. And compare back to the method of joints, these four were all positive values, meaning they were all in tension. If you want to thank your TA Serenity for being a big help, go ahead and hit the thumbs up button. And if you want to see a method of joints, method of sections example problem, go ahead and click the video that's up on the screen here.